I'm Garrett Smith. I've been going to this conference for quite a while, back in the original, I think the inaugural conference, when it was, I believe, called TechMesh. And it's undergone a couple rebrands. And it's great to be back. Thank you, Francesco, for the invite. So my background is in systems. It's systems and software, distributed systems. I ran operations for CloudBee's platform as a service prior to starting this company, Guild AI, a couple years ago. So I'm talking to you as a programmer, as a coder, as a hacker. And I'm going to introduce this topic of artificial intelligence engineering. And it is a rather loaded term. We're going to talk a lot about what this term means and what AI engineering means. And the term AI engineering in this talk is a little bit of a hook to get you sitting in the seat. As it turns out, I'm going to recommend that you not call yourself an AI engineer. Sometimes I call myself an AI engineer, but as we'll see, that is a very, very tricky topic. And the goal of this talk is going to be to introduce this cross-section of traditional research and application in artificial intelligence and traditional engineering, software, systems, disciplines. So it's kind of a vehicle for that content. So there's this concept of AI when you say AI, what does it mean? I mean, for a lot of people, it means the end of the world. It means the singularity. It means computers learning recursively in a positive feedback loop and bypassing human intelligence in the blink of an eye and all of a sudden conquering the universe, filling it with paper clips. Somebody misprogrammed it and all of a sudden the universe is full of paper clips. That is definitely a version of AI, and it's in reference to artificial general intelligence. And it harkens back to 1955 at Dartmouth when John McCarthy and a number of researchers, scholars in many, many different disciplines came together to tackle this new thing called artificial intelligence. And the charter for, I'm going to read this, the charter for that meeting was this. The study is to proceed on the basis of the conjecture that every aspect of learning or any feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made, this is what the gathering was to do, an attempt will be made to find out how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. And this was the first definition of artificial intelligence, and I think it stands today. I think this is serves as the working definition. But I'm not going to be talking about that goal. That is a general intelligence goal. And AI, as we'll see, can be used to describe things that are far more practical and actionable and direct line of sight achievable within not just our lifetimes, but within days or weeks or months of having left this room. Before I get into that, I want to just cover this really huge range of disciplines, and it's what kind of attracted me to the area. There's a lot of technical advancements in the last few years, last 5 or so years, that have been technically very attractive, but for me personally, this is such a cross-discipline of so many different fields. You have cognitive science, sort of neuroscience and anthropology, philosophy, and we heard about ethics in AI this morning, and just very high-level topics. And then it lowers down into some of the physical sciences, social science, and then the things that we're going to be talking today about, systems, computer science, and mathematics, some of what I would describe as more concrete. But all of these are part of AI. This is to show, though, that AI is extraordinarily broad, and it's very difficult, even at the highest level, to really pin it down. What are we talking about when we use these terms? So I am not going to be talking about the AGI, the artificial general intelligence. I'm going to be talking about intelligent systems. Now, this is something we've probably heard a lot more of. So this emotional loaded term AI, I'm going to boil this down to, or reduce it to intelligent systems. And this kind of harkens back to the 80s and 90s of expert systems. And people have been doing this for a long time. So there's nothing new. So let's ground ourselves in recent history and in deployed applications and in concrete work. And we're going to talk about those things. I actually like to use this term, which is hyperautomation. I don't hear a lot of this talked about, but I think this strips all the bugaboo or the emotional content out of that. We're talking really about automating something that was otherwise very, very difficult to do. And we'll see some examples of this type of hyperautomation. Now, we're not talking about super intelligent computers here at all. We're talking about solving basic problems. We're just doing it using levers and tools and techniques that are fundamentally new and fundamentally more effective, superior to previous methods. And that's a big deal, whether we're talking about supercomputers, super intelligent beings emerging from our silicon or not. So the first foray into this is this discussion of data science. This is an old Venn diagram by Drew Conway. Did I get this right? Yeah, Drew Conway. That it has a little tongue-in-cheek content to it, but it's useful. If you see Venn diagrams associated with data science, they all stem from this. There's actually a coverage of the history of the Venn diagram associated with data science. So let's take a look at this. Conway in this is basically breaking down data science into three overlapping components. Hacking skills, which is sort of what would be associated with this conference. So programming, software, systems, the things that we're used to doing. Math and statistics, the things that I find intimidating. I'm not a mathematician or a statistician. This is an area that requires multiple years of graduate level work to have practical skills in these areas. It is not something that you just dive into with a tutorial or a quick read. It's a significant investment in learning. And then what he calls substantive expertise is really domain experience. And you have a cross-section or an intersection of these things, which creates this field of data science. But I want to be even more specific than data science and start to talk about machine learning. Because as we see the breakthroughs in AI, so-called, are really breakthroughs in a particular domain, largely a breakthrough in a particular domain of machine learning. So I'm borrowing here, or stealing directly, rather, from Pedro Domingo's The Master Algorithm. And I recommend this at the end as one of the books to read as an introduction to the topic of machine learning. Domingos breaks down machine learning into five, what he calls tribes. There's the connectionists, the symbolists, the evolutionaries, the Bayesians, and the analogizers. And in the book, he goes through each of these tribes in a fair amount of detail. And when you read it, you get an excellent coverage of this field at large. What he's trying to do in the book is synthesize these and draw from each of the tribes to create what he calls the master algorithm. And the master algorithm is sort of a vision of a single learning algorithm that takes the best, the most fundamental capabilities of all these tribes and synthesizes them into one thing. But that's not what I want to talk about. From the book, he breaks down each tribe in three areas: representation, evaluation, and optimization. And I'm going to show you this. And don't try to absorb this in one blow here. What I'm doing with this slide is I want to introduce sort of the depth, the range of fields within the field of machine learning. The representation, so over here we have representation, then we have evaluation and optimization. Representation is how do you represent the scope, the problem domain? How in this particular tribe do you model something? This comes down to representing whatever it is you're trying to solve. And each tribe has a different language or different mechanism, different structures rather for representation. So symbolists have logic. The connectionists, which we'll talk about in more detail, have neural networks. So put an asterisk next to this. The evolutionaries have genetic programs. Bayesians have graphical or Bayesian models, networks. And the analogizers have support vectors. And each one of these things is a very, very deep field of research / applied research. And it's broad. We like to talk about neural networks all the time, and I'm going to spend a lot of time talking about neural networks. But we're really covering a great range of things. And when we're talking about sort of AI in general, it's important to be able to draw from what's actually out there and not just focus on the neural networks, which we're going to do. Okay, so the evaluation is, once you have the representation, how do you measure goodness? How do you measure the quality of what you are representing? And again, each tribe has a different, we have accuracy for symbolists, we have squared error, mean squared error, and within each of these, this actually blows up into a whole field of research. Fitness for genetic programs, the posterior probability for Bayes, and margins for sport vectors. And finally, there's an algorithmic component, which is the optimization. So we have representation, we have how do you measure goodness, and then finally, once we know how to represent and measure goodness, how to maximize goodness, or how to minimize badness. So we have these optimizations, optimize high or low or whatever it is. So in this case, it's an algorithm of inverse deduction for symbolists. For connectionists, it's gradient descent. And there's actually a whole bunch of other ones. Genetic search is the algorithm that is largely used in the evolutionary the genetic programs. Probabilistic inference for Bayesian and constraint optimization for sport vectors. It's big and it's broad. And you could spend your career on a very, very small subset of any one of these boxes. And the reason I'm mentioning this is you need to take a step back before you dive into this field of AI and realize that it is a tremendously broad and tremendously deep field at large. So much so that it's almost ridiculous to talk about. You need to be very specific about really anything and everything. Now that said, don't be intimidated. There are ways to move forward. And we'll see as engineers, as programmers, at the end of the day, we have the advantage of actually building running software. And running software is pretty powerful in light of anything else, because it's actually running. We're marshalling electrons, we're doing work, and that goes through the field of engineering. But nonetheless, this is sort of the backstory of AI, and in particular, well, really machine learning component of AI. So we are in a hype cycle, and it's what got me into this. And this was a couple of years ago, which is kind of the middle of I don't know when this hype cycle will end. What we're looking at here is, does everyone know what arXiv is? A-R-X-I-V? Anyone not? Yeah, or anyone know what it is? Okay, so not. So arXiv is a repository of freely available academic papers hosted by Cornell University. It's kind of like GitHub in that it sort of has become the de facto standard to put stuff. In this case, the stuff is papers. So you consume PDFs, and they're academic papers. They have the standard paper format. And it's so ubiquitous, it serves as a solid source of measurement for particular fields, research and production in particular fields. So we're looking at the artificial intelligence category in arXiv. And you can see it's exponential growth at this point. It is going to be an S-curve. We can't have unbounded growth because there's only so many people on Earth. But where on the S-curve are we? S-curve meaning at some point it's going to taper off. But where are we in that S-curve? Anyone's guess. But it is spectacular growth. And a lot of this is just we'll see is the advent around 2012 in deep learning, in particular convolutional networks, and in the development of sort of the progress between 2012 to 2015 or so, caused so many breakthroughs and generated so much publicity for this field that it has attracted basically everyone's attention. So it is very popular. This is the same search for the machine learning. This is both of these are under the computer science category. So these are fields of subcategories within arXiv of computer science. The machine learning is essentially the same. The axis is the same, so it's 1400, right? 1400. It's essentially measuring the growth of machine learning in this case. So take it for what it's worth. It's arXiv. There could be some bias there. I don't mean to slight other areas of AI that are not machine learning. But when we're talking about machine learning, certainly this talk, we're talking about AI. In this talk, we're squarely talking about machine learning. And within machine learning, this is computer vision. So this is pattern recognition. this is 1,000, so it's not quite all of, but it's a significant chunk of the published content on arXiv in the field of computer vision. So again, the network, the neural network, and specifically the convolutional neural network that is associated with computer vision is driving a lot of this interest. So we'll cover what I'm talking about there. Finally, just to show you and to prove without any doubt that we're in an extraordinary period of growth and interest. Well, these are papers, so this isn't more than just interest. These are people who are publishing content. This is NIPS. This is the Neural Information Processing System conference. It's the premier sort of neural network conference, and if you go back through its history, much of the drama that's played out in the history of AI, so-called, has happened at this conference. So it is squarely in the connectionist field at this point. Again, tremendous growth in the field. Okay, so deep learning is driving this interest, and we're going to talk about what that is. So the deep learning, some of the notable advents here. At each one of these, you've got Alexa, you've got sort of the home device, and this is sitting in people's. Who has Alexa? Anyone? I'm so very nervous about Alexa. I was in somebody's home who had Alexa, and they had a very dysfunctional relationship, or this codependent relationship with Alexa, and was shouting at it. And as good as Alexa is, I will always remember this conflict that this person had with Alexa, and I'll just be like, I want nothing to do with that. But this is in people's homes, and it's using deep learning, and it's real. This is not. I mean, these are being deployed and used, in production, so-called, in this case, a consumer electronic device. This is Lee Sedol, losing, though brilliantly, to AlphaGo. The real story here, from my point of view, is that while he lost, he used about 1/40,000th the power that AlphaGo used. So the human brain is still far, far better a computing instrument in terms of output per unit of power by many, many orders of magnitude. But anyway, this is a famous milestone in history of artificial intelligence. And of course, Waymo's autonomous vehicle, which sort of represent the icon of autonomous driving, autonomous vehicles. These are real applications, and each one of them makes extensive use of deep learning. So what is deep learning here? So if we look at this sort of very high-level summary, I've called this AI methods. It's more than just machine learning, but we're going to be talking about machine learning, and then within machine learning, we're going to be talking about deep learning. And this is the connectionist camp. And the reason I even talk about this is a lot of times people will just automatically associate deep learning with artificial intelligence. Like, artificial intelligence is deep learning. That is not the case. If you go to Domingo's book and understand the breadth of approaches to machine learning specifically, there are trade-offs galore across all those different tribes and methods. And the reason that these are vibrant, growing camps, these tribes, is because they're bringing valuable options to the table. And if we're talking about AI engineering, we need to be aware that it isn't all deep learning. But I'm going to pick on deep learning simply because it's that engine, it's that lever that's sort of getting us here and getting our attention. It's like all of these advents, all of these breakthroughs are really very much a result of what's going on in deep learning. Another internet borrowed diagram, and I'm absolutely not going to go through this. The point of the slide has nothing to do with the slide content at all. The slides will be available, and if you're interested, you go to the original content, of course. You can go and map the flows, but this is a very, very good diagram that covers a lot of great content. But this is not the point. The point of this story is, this slide, is that when I got into this, because I borrowed it from the internet, and I attribute it, so it's true borrowing, I'm not misrepresenting. It bothered me that it was hard to read this text. And so I used the great open source tool GIMP, which is kind of like Photoshop, but open source are better. And I applied a sharpener filter to get to that. And I wasn't really happy because it's worse. So this is the original. So again, don't worry about don't try to figure this stuff out. Different story. This is a bait and switch. So this is pretty bad. This is kind of worse. So I thought, well, there are models out there that are pretty good at sharpening photos. I wonder if I could just use an AI software component, a trained neural network that knows how to sharpen an image. And I got this. Now, I don't know what your opinion is, but when I looked at this, I was very disappointed because it's basically the same as that. It is sharper, and it is state of the art. This is certainly better than the unsharpened filter that I used. And it is clear, but it wasn't like, oh my goodness, I can't believe that. And the point of the slide is that this work that we do in so-called AI is largely underwhelming. It's like excitement, I can do this, and then you apply it, and you're like, okay, yeah, I could see where that might be useful. Not that great. And it leads us to, let me give you quick credit to this project. This is on GitHub. It's Neural Enhance. It's from a Theano library, which I'll cover. It looks like I'll have time. And it basically takes an image in general and sharpens it. So we can see sort of the underwhelming results, and you know, it's good. It's pretty good. So Piccadilly here, you can see the text, and this is what inspired me to use it. I'm like, well, that's great. It's going to make that slide really pop, and everyone's going to see it. But it's okay. And my immediate response was, I wonder how we can make this better. So I want to talk about a methodology that I use and basically everyone uses, and it's basically the cornerstone of all innovation and technology. It's basically, I've just spit out the empirical method. You propose a hypothesis, a problem, right? You run some experiments, you measure that, and then you refine and feed back into the problem definition in the experiment. Does this make sense? Is this like intuitive? Everybody does this all the time. And the point here is that there's nothing special about work in AI. It's all the same thing. Underlying this process, however, are some very important points. Number one, in the area of, in particular supervised learning, in particular machine learning and deep learning, data is far, far, far more important and scarce than any of the sort of the technical components that we'd be tempted to think with these barriers of knowledge or what algorithms do I use, what methods, where do I get the compute resources? The problem is always data. Google has a problem with data. Facebook has a problem with data. Baidu has a problem with everybody, no matter how big you are, has a problem with data. There's always a reason to get more data. It's part and parcel of the methodology. It consumes data. And insofar as you have data, you can solve problems. If you don't have the data, you really can't. So when you go about trying to identify the problem that you want to solve with all this great new stuff, you have to consider, what data do I have? What data can I have? And if the answer is nothing or not a lot, you've got to cross whatever problem, you've got to cross it off. Don't try to solve a problem for which you don't have data. And of course, that takes expertise to analyze that. But this is we'll learn this is the great equalizer amongst players here. Also underlying it are the models and the algorithms. This basically goes back to the representation and the optimization. And the question there is, what is out there? What has the field of research produced that I can use? Or if you want to go ahead and spend 6 to 18 months on novel research and roll the dice there, I wouldn't do that as an engineer, sort of almost by definition. You are, as an engineer, somebody consuming something off the shelf, you are constrained by the models and algorithms that are available. And then finally, the compute. There are some problems that require extraordinary compute, and you may simply not have access or budget to run that. So while this is a very straightforward process, it is constrained mightily by these three areas. And when you think about doing any work in this field, you think in terms of these constraints all the time. Quickly going back to this, my hypothesis, right, so my problem, my speculation, is that this model has been trained on photographs. I'm interested in, really, in sharpening text. So this was trained on the wrong data. And while it did improve things, it improved things very, 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 very little. And what I could do is I could synthesize data by generating using sort of the using vector rendering, your text, postscript, whatever, generate low-resolution images from that, and then distort those algorithmically. It's called data augmentation. So I can synthesize a huge training set for this. So I'm not really constrained by that, just a matter of running it. And then you train the model comparing the low res to the high res, and in time that model will get very, very good at making this text crisp. And that would be interesting. I'm probably not going to do that, but that's what I would do if I. So in this case, I'm going to run an experiment. I'm going to see what happens. Does it work? Common sense, but again, constrained by these three things. So in this field, and this is really a breakthrough conceptually, but this aligns. I got these 3 roles. These are job roles in big companies that have, say, AI programs. They wouldn't call them AI programs. It's for all the reasons sort of become obvious at this point. It's a bit ridiculous to bandy, to throw the term AI around casually. So it might be a deep learning program. It might be a machine learning program. It might be something specific, autonomous driving unit. But by and large, these 3 roles come out consistently. You have the research scientist. The research scientist is a pure researcher, and their output is a paper. And they're not tasked with shipping code. Often they don't ship code. They may have used some code, but you rarely, or you sometimes don't get access to that. So you're basically interfacing with research through the reading of paper. And what do you do at that point? We'll talk about that in a minute. The other role is a research engineer. Let me actually skip down here. So we have a research scientist, and then we have a software and systems engineer. This is pure software systems. This is what we do at this conference, traditionally. So I don't need to explain that. The research engineer is sort of an in-between role that is pretty closely aligned. It works closely with the research scientist, but they're tasked with solving the technical problems, implementing the algorithms and the models and the theories, whatever the scientist proposes, often feeding back tightly, work tightly with this. This is probably out of reach for the role that I'm talking about. These could be interchangeable human beings. What I'm talking about in this AI engineering is really sort of an overlap here. And I'm going to be very specific about how that's done. So I know this is a bit amorphous at this point. But when you go to these companies, you can say, what's your role? And they'll give you a name that corresponds to one of these things. Of course, research engineers do dip down into. But this is probably the closest thing to an AI engineer. And I would probably at this point just say, don't ever call yourself an AI. I don't really say I'm an AI engineer. I would feel very insecure about that. I am really sort of this person with some of this and moving increasingly up into this category. But without doing serious graduate level work in a particular area, you can't touch this field. I mean, these folks all have PhDs, sometimes multiple PhDs, and you're talking about a 2 to 6+ year burn in learning curve. So as we'll find out, though, it's okay to be here. There's no reason to feel insecure at all. So I like to think of this work in terms of a funnel with the research contributions at the top. So these are the papers. And then you've got the next stage is to take a paper and implement it. Who's here has implemented a paper? So you take a paper, pretty common in computer science to say, I've got a problem, what's state of the art, what could potentially be applied here. You go read the paper. Of course you can't install it, you can't clone it, but you read it, you reason through it, and then you implement it. You might have to contact the original author to get some feedback or have some questions, but you've got this process of implementation. So the research in this field, if it makes it anywhere, is going to get implemented. And this is a special set. For me, and I'm not embarrassed to say it, I don't have the chops to read and understand all the content in these papers. I actually measure my progress by how deep into a paper I can read before I just stop understanding anything. You can almost always get through the first paragraph because that's the problem definition. And you can almost always read the concluding paragraph because that's the summary, which restates the problem definition. But in between that is a minefield of representations and concepts and ideas that are advanced for me. And to be honest, talking to folks who are even doing the papers, a lot, in many cases, it's difficult to read a colleague's paper because it's either so specific or it's just badly written or what, this is a challenging area to go and extract and apply. But nonetheless, this is what this tier is. So you have, and not all papers are implemented, thus the funnel. And then here we have this application, which is taking code that works but was not necessarily designed for when I say application, I mean I'm going to apply this to a sort of production problem. And in between here, I've injected pre-trained models. I don't know if I want to cover what that is right now. I don't think I do. I don't think I have time. But there is a component here which will influence your decision as to what you may adopt. Very quickly, a pre-trained model is basically taking the representation, applying that optimization algorithm to it using data. So you're actually training the model. It is domain specific. So you train a model with a particular set of data or for a particular type of problem. And then that pre-trained model becomes useful in some application. And if there happens to be a pre-trained model that is perfect for your application, you can just take that pre-trained model and apply it and use it. And in particular in computer vision, that is very, very common. So you say, oh, is there a pre-trained model for this particular network architecture? And what was that trained on? I was trained on ImageNet. Okay, great, I'll go use that. I'll see how that works. So that's a point of consideration in this funnel, this acquisition of knowledge and resource. So here's an example of the best paper from CVPR, which is a computer vision conference. This happened to win best paper this year, the taxonomy, disentangling task transfer learning. And we can probably all get through this abstract and see what the pictures are, and then you'll see the mathematical representation, and that's where I start to fall over. I'm working on that. I want to be able to get to that point, but there's a lot of growth. That's the paper. There happens to be a GitHub project for this. So you can take the implementation of the paper and actually clone it. You got the code. You can study the code. Which is really nice. You can then mirror and have a connection between the content of the paper and actual working code that you can even step through if you need to. You can really reason about how something is implemented if you want to. And then the third area, this application, they happen to have an application running. So this is taking their library, their paper implementation, and they built a website so that you can go demo what they built. So this is the life cycle. You've got sort of the upstream research, you've got the library, the implementation. You might have to clean this up and change it and adopt it to your particular task, and then you apply it as an application. In this case, that's a web app. But this process is AI engineering, whatever you call it. It is the act of taking new stuff, solving problems that have never been solved before. And if your problem happens to align with that, you will have an advantage for a period of time over your competition. I'm talking sort of businessy here, but whatever it happens to be, whatever you're interested in. This field is churning out state-of-the-art, performant research / code / other artifacts that can be applied by you, by me. That's this process of engineering. And this is the process that I go through all the time in the work that I do. Okay, let's talk about some specifics here. I wish I could put Erlang up here. I wish I could put Haskell, or I'm predisposed to functional languages, so I'm going to be biased. I'd say other languages, but I wouldn't want to see them up there. Actually, JavaScript has shown up recently with TensorFlow for JavaScript. But Python really is the language in this field. It is not the language. So let me break this down. High level. Python, C, C++, you might say assembler, but this is associated with device, lower level platform APIs. Unless you're doing this work, you'll never work in C or C++. But if you do this work, or you are working on a performance problem that requires you to get down into a kernel level, you'll be using that. And then everything else you know, That's the application part. So how do these things get deployed? Well, at some point, they might be run behind a web server. What web server do we use? All right, that's a breadbasket. That's how we know. But not knowing anything about neural network models or inference or the performance characteristics of some of these things will be a problem. So you do need to understand the upstream mechanisms here. But everything you know will apply. Okay, so within Python, these are the frameworks that are really on the map. I may have left out, I don't think I've left out any major ones here, but there's a churn of new libraries that are always being produced. The question here is the same question that you would answer with, what database do I use? How many database options do you have for any given problem? If you really understand your problem, you might have 3 or 4 pretty good options today. If you didn't understand your problem, you probably have 40 options today. So you want to understand your problem. You understand what these libraries do vis-a-vis the others. It's the same architectural engineering discipline that you apply to anything else. And that's what makes this field accessible as a discipline to engineers, for engineers to enter, is that at the end of the day, we're working with code. It runs on computers. There's nothing new under the sun here. The problems that are being solved are novel. And there's some supercomputing components going on here, so that's kind of cool. But at the end of the day, it's about libraries and application. These two areas break down into a couple of high-level areas, training and inference. So in machine learning, as we sort of hinted at, there's a training process. As you learn a model, as you learn weights, whatever your representation is, that machine learning process involves training a model. And the underlying platforms that we have today primarily are GPUs. So you cannot do this stuff. In the deep learning category, you cannot work without a GPU or an accelerator of some type. You cannot run on out-of-the-box CPUs. It's just a matter of fact. If you want to get into this stuff, you either need to appeal to cloud services or invest, and it's a nominal investment these days, in a GPU. This laptop that I have has a GPU, but it is not usable for anything. I mean, I can make sure that things run like one step, and then I have to stop it. You really need a dedicated machine. So there are really good options here to get started. So what I mean by ad hoc GPU server is just a server that you get. Build it. Put a GPU in. Oh, I've got my GPU server. A dedicated multi-GPU server is something that is something you go and make an investment in. And this is a supercomputer. The DGX-1 from NVIDIA is by all accounts a supercomputer. It's about this big, and you can I think it's $130,000. I'm not sure what the price is now, but it's a 6-figure investment. If your organization does this all the time, maybe it's a consideration. I think for most organizations today, though, cloud options are very, very good. If you want to get into this to start, cloud options are very good. You can spend tens of dollars and make some progress, hundreds of dollars to make really good progress. And this is sort of renting GPU time. Amazon's great. I have direct experience with Amazon, Google, CloudML. Anyway, these are options that you have. For inference, you'll see this word inference a lot. It means that once you have a trained model and you want to apply the model, you want to run it, and you want to use that model to make inference. So you take inputs, push it through the model, and outputs come out. And that's usually done on device, so telephone. I want to go say, what is this thing? Boom. It classifies it. It measures it. It does something interesting with it. That's inference. And as an area of engineering, this is quite interesting. There's a lot of innovation going on this front. Apple with Core ML, for example, has really done some amazing work with their devices, the iPhone platform in inference. But this is changing constantly and evolving. So if you're an embedded device person or a device person, applying your skill set in this area is pretty fun. It's all gearhead stuff, and it makes a huge difference. Because at the end of the day, all of this work eventually lands in an application, and the on-device embedded systems is sort of the logical, is a very sensible component for much of this. Think about an autonomous car. Right? You can't really run they do run servers, but they have to be very, very aware of power consumption, heat. So it is in a constrained environment. So it's sort of the domain of a device, of embedded systems. Okay, so I'm going to wrap up. Takeaway number one, if you're approaching this, do not approach this thinking that you're going to be an expert, the full stack developer in this field. You're not going to be. You can get through a lot of stuff, but the upstream content, the models, the mathematics, the statistics, I think you're going to have to sort of let your eyes kind of glaze over. Unless you're, maybe I'm wrong. I think practically though, for most of us, we're going to want to focus on installing software and running software and building applications, the same thing that we've always done. We face a problem here. This is what I call the floating city problem. Some of the problems here, frankly, the competitive differentiator of having lots of data and having lots of compute is profound, to say the least. And there are some organizations that have these. This is just one small clip of a huge data center with specialized hardware for training and doing inference. And the investment that goes on here is fantastic. If as a small organization or as an individual, you really cannot think about competing with certain problems. However, this is a reference to 1992. James Carville, it's the economy stupid, really meaning, I don't know if anyone has been around long, I mean, many of us have, but it was this, the economy stupid, it's what got Clinton into the, anyway. It's reference to that. It's really the data here. If you have, either as an individual or as an organization, have access to data that is proprietary and unique, that is your comparative advantage. And as long as nobody else has that access, you will be able to do things with that data that no one else can do. And so the question is, do you have the data, or how could you potentially get the data? So if your organization has a large customer base, of course privacy issues and all of that in play, that really will allow you or an organization to build interesting and unique technology. The algorithms and the compute and the resources and the knowledge for applying that is pretty commoditized at this point, but the data is not. All right, I'm not sure I have time to go through this. Maybe I do. Hit the highlights here. So if you're an individual here, go build something small. There's tons of tutorials out there. You can go run through them and get your hands, get some experience with that. And also find somebody that you can talk to about this. Just go online, or if you happen to know somebody, just talk to them and start a dialogue. Start that process. Don't be intimidated. It's a huge learning curve, but you've got to start, and you will make progress. If you're a company, very similar approach. Lower expectations. Don't expect that AI is going to transform your organization. Define something that you expect to fail and get some experience with it. If you have the budget, you can go hire a data scientist. You can build a program. Not many companies that I know go do that, but you can always put forward an idea for an application, a prototype, and build that out, and that's how you build experience within your organization, and that works. 3 books that I recommend. I only have 3 here. There's obviously more than 3 books in the world that are very good, but these are very, very good for getting started, and they provide different things, but I have them listed here. You can look at that online, and that's sort of the underlying call to action here. Go build something, even if it's just a toy, even if it's just something to experiment with. And you will start to build your resume as an AI engineer, keeping in mind that that's probably not what you want to put on a business card at this point. All right, that is my introduction to AI engineering, the role, and I think I have time for a question.
Okay, who's going to be first?
Oh, yeah. Oh, that's a great question. Thank you for asking that. So this is an open source tool that, so this is an open source tool that automates TensorFlow workflows. So it really is at the center of what we're talking about here. And it's for engineers to go build things very rapidly with a tool-oriented focus. So it's not high level, it's low level, very POSIX-y. You're editing text files, you're running commands, but there's a lot of automation that goes on, and it speeds the productivity of the work that you would do in this field. So check this out just to see what it is, but also we're building a community of people who are doing this work, this sort of intersection of machine learning, mathematics, and the application of it in engineering.
As an individual, I'd like to go and try out AI, but as you say, it is all about the data. So one of the problems is that all these tools are available and they're all amazing. I can go and get Python and all the AI stuff, but where do I get my data? Because companies are a lot more secretive about what data they've got than they are about open source, which is now a really big thing.
So I would repeat the question, but everyone heard it. Any tutorial that you see online will have data for you. And generally, it's a toy data set. It's very small. If you're lucky, you'll be able to take that and apply it with another data set that's online. So there's generally available data sets. But what I would say is don't worry about that. Go, and these will all be online. Pick an area here, and then just Google that and find a tutorial. And it could be in any one of the libraries. TensorFlow is very popular, but the other ones are very good as well. But find a tutorial and go with the tutorial, whatever it recommends, and then just go into it. And you'll start to answer those questions directly. But in all these cases, any of the tutorials will have data sets for you.
Thank you.
Oh, it's red. Okay.
We don't have time.
Yeah. Yes, indeed. Thanks.